Hi everyone, welcome back to Kim Help ASAP. Today we're going to be talking about rainbows. Well, actually, rainbows is a small part of what we're going to be talking about. We are going to be talking about the electromagnetic spectrum. And yes, the visible spectrum is part of that electromagnetic spectrum. However, we are going to expand out of the visible light section, and we're going to talk about microwaves, we're going to talk about X-ray, and we're going to talk about ultraviolet light. Let's get started.
Let's start with a broad definition of what electromagnetic radiation is. This is how energy travels through space. All of these forms of energy, whether again they're light from the sun, they're X-rays, or they're radio signals, are waves. So this is a common characteristic that they share, is that they are all waves. Okay, so we need to then think about and talk about waves. So there are three main properties of waves. There is the wavelength, which is symbolized by a lambda. This is the distance between two peaks or troughs in a wave. So let's show this on a generic wave. So here is my generic wave. If I wanted to measure wavelength, again, I need to measure the distance between either two peaks or two troughs. So I can measure the distance here between two troughs. This distance is going to be your wavelength or your lambda, or I could take two peaks, measure the distance, and this would give you the same thing. This gives you the wavelength, which is lambda. The next property of waves is the amplitude, represented by an A, and this is the magnitude of the wave's displacement, or, which makes more sense, half of the height of the wave. So let me show this on our generic wave. So if our total height of the wave is from peak down to where the trough would be, amplitude would be half of that. So you could measure from peak down to halfway, or you could take from the trough halfway up, and that would also be the amplitude. Last, we have frequency, which is represented by nu, which looks like kind of an italic V here. This is the number of waves or cycles that pass a specified point per second. Now, frequency is often measured in hertz or 1/seconds. This is not something that I can draw on a static wave, but something that I hope you all have experienced. So imagine you're at the beach. You are the stationary point, and the frequency is how quickly are waves passing by you. So they might be passing by you very frequently, or maybe you don't have that many waves and they're not passing by you very frequently. That is the frequency. So let's see what it looks like to draw different waves as we change up wavelength, amplitude, and frequency. So going back to our standard wave, let's change the wavelength. So let's make it a very long wavelength. So now my wavelength is, again, if I measure from peak to peak, is this distance right here. Now let's see what it looks like when I change up amplitude. So if I make the amplitude very large, it's going to look something like this. Again, my amplitude is from my peak down to halfway, or I could measure from my trough, again, up halfway, and that would give me my amplitude. Okay, but what does it look like if I change the frequency? A high frequency wave, you're going to have a lot of peaks and troughs in a very short space. Again, if you're at the beach and you've got really choppy water, these waves are hitting you often. So you can think of frequency as either maybe compressing this wave like a spring down, or maybe stretching it out, which would give a low frequency. So when we talk about the electromagnetic spectrum, most people immediately think of visible light, which is absolutely part of the electromagnetic spectrum. It has a wavelength that goes from about 4 × 10⁷ meters to 7 × 10⁻⁷ meters. And all of these different wavelengths represent different colors to us. However, what I want you to understand is your visible light is actually a very tiny slice of your whole electromagnetic spectrum. And actually, it goes farther than this. So what we experience is actually really, really, really tiny right in there. So we have wavelengths that are very, very small, so down in the gamma range, all the way up to radio signals, which are really, really large wavelength waves. Now, there are relationships between wavelength, frequency, and energy. Okay, so here is our summary of these relationships. So as you increase wavelength, you will be decreasing frequency. As you decrease energy, you will be increasing wavelength. And you can see this representation on the bottom here is showing how the frequency is very high down here. The wavelength is low. But up on the right-hand side, you can see the wavelength is very long, but the frequency is very low. But let's actually get mathematical expressions to describe these relationships. Starting with wavelength and frequency, they are related by this equation right here. So c is the speed of light. So you'll see at the bottom of the page here, c is the speed of light. That is 3.0 times 10 to the 8th meters per second. And of course, we have wavelength and frequency. So if we know wavelength, we can find frequency. If we know frequency, we can find wavelength. Next, we have a relationship between frequency and energy. So E here is for our energy, and H is actually Planck's constant. You can see it right down here. This is a very, very tiny number. This is a joule times second. Those are the units there. And finally, our relationship between wavelength and energy. If I were to solve this top equation for frequency and plug it in right here, then I would get this equation right here where energy is related to wavelength. So as long as you have these first two equations, it's pretty easy to derive this third one. Okay, let's do a quick example where we work through some math. So our question is, what is the frequency of an X-ray with wavelength of 1.35 nanometers? So we have been given wavelength and we want to calculate frequency. So looking at my three equations I have on the left, I'm going to want to use this equation right here. So let me just write that down. And let's plug in what we know. Well, we know c, that's the speed of light. We always know that. So that is 3.0 times 10 to the 8th, and that is meters per second. This is going to equal our wavelength, which we do also know as 1.35 nanometers. And we are calculating our frequency. Now, hopefully you have spotted our problem. Our speed of light is in meters per second, but our wavelength was given in nanometers. These units are going to need to match so that they cancel out. So you can either change the speed of light to nanometers per second, or you can change your wavelength to meters. I'm going to change my wavelength to meters. So I'm going to do a quick side calculation here. If I have 1.35 nanometers, how many meters is that? Well, there are 1 times 10 to the 9th nanometers in 1 meter. So that gives us 1.35 times 10 to the negative 9th meters for this wavelength. That's a fantastic thing about using the SI system and the prefixes is it makes this conversion really easy. Okay, back to our problem. I'm going to rewrite this with our new converted wavelength n, 1.35 times 10 to the negative 9th. That is now meters. I'm going to solve for frequency, and I get a frequency that is 2.22 times 10 to the 17th. And of course, this is 1 over seconds, which you can also write as hertz. So these mathematical relationships are fairly simple and they're not very complex, but where I see students having problems is with the units. So watch your units. And again, the most common thing is your wavelengths are not in meters. So just again, be aware of your units and make sure that they are matching or canceling like you need them to cancel.
In our everyday life, we usually think about light as just being the visible spectrum, but now you know how broad that electromagnetic spectrum actually is. And the next time after a storm you see a rainbow in the sky, you can think about how those wavelengths and frequencies are different, and that's how we perceive color. I hope you found this video helpful, and thanks so much for watching.